Welcome. In this video, we'll be analyzing probabilities of dependent events and tree diagrams. Let's take a look at our first example. Example 1. A box of chocolates contains 7 milk chocolates and 5 dark chocolates. You randomly pick a chocolate and eat it. Then you randomly pick another piece. What is the probability that the first piece is milk chocolate and the second piece is dark chocolate? Okay, to solve this type of problems, we can always use tree diagrams. So let me list my first outcomes, or the outcomes for the first chocolate. I have milk chocolate, and I also have dark chocolate. Now notice that since we have 7 milk chocolates and 5 dark chocolates, our sample size is 12, 7 plus 5. But when it comes to the probability of getting milk chocolate, it's 7 out of 12. And for the probability of getting dark chocolates, it will be 5 out of 12. Now, let's see what are the possibilities for your second chocolate. Still, you can get milk chocolate or you can get dark chocolate. Even for this one, okay, let's say you eat dark chocolate. For the second one, you can still eat milk chocolate or dark chocolate. Now, probabilities change given what occurred in terms of the first chocolate. Let's say you actually ate the milk chocolate on the first one. Then that leaves you, instead of 7 milk chocolates, you only have 6. And instead of 12 chocolates, since you already ate one, you only have 11 left. Okay. With the dark chocolate, even when you ate the milk chocolate, you can still have 5 dark chocolates out of 11 total chocolates. Now, let's say you actually ate dark chocolate for the first one. That leaves you with 7 chocolates that are milk chocolates divided by a total of 11 chocolates. So 7 11ths will be the probability of getting a milk chocolate. And dark chocolates, you already ate 1 out of the 5, so you are left with 4. And instead of 12, you are only left with 11 chocolates. Okay? Now, here, what we're interested in is in the probability that the first piece is milk chocolate and the second piece is dark chocolate. So let me write that down. I want probability that the first one is milk and the second one is dark. So using my tree diagram, I analyze this case, milk and then dark. So I just multiply the probabilities. I have, this is 7 12s times 5 11ths. Okay, using basic probability, 7 times 5 is 35, and 12 times 11 it's 132. Okay, so that's the probability. Now, that's using your tree diagram. You could also have used the formula for that. Okay, we can say the probability of getting milk chocolate and dark chocolate should be the same as the probability of getting milk times the probability of getting dark chocolate, given that you already had milk chocolate for the first chocolate. Okay, and if you notice, the probability of getting milk is still 7 12ths. And once we actually know that that occurs, the probability of getting dark chocolate is 5 11ths. And you still get the same answer as before. Okay? So in general, when you're solving for problems that deal with dependent events, you can actually use a tree diagram, or you can use this formula. The probability of A and B, or A intersection B, is the same as the probability of A times the probability of B, given that A has occurred. Okay. Let's see another example. Example 2. There are 8 shirts in your closet, 4 blue and 4 green. You randomly select one to wear on Monday and then a different one on Tuesday. What is the probability that you wear a blue shirt on Monday and a green shirt on Tuesday? Again, let's go ahead and list our outcomes for Monday. You can wear blue or green. Notice the probability of getting blue is 4 out of 8. How do I know it's 8? Because it's given to us that we have 8 shirts, and 4 of those are blue. In a similar way, we know that we have 4 green shirts, so we write 4 out of 8 for the probability of getting a green shirt for Monday. Now notice this is just a half, so let me just simplify that one to a half for now. And let's see what happens on Tuesday. You chose a different one. That means whatever you used on Monday, you can discard. So still, you can choose from blue shirts and green shirts. So let me write that down as the next level in my tree diagram. And let's see what happens with these probabilities. Say you actually wore a blue shirt on Monday. So you no longer have 4 available, you only have 3 out of 7 shirts. But since you wore a blue one, that means that you still have the 4 green left. So the probability of getting a green one will be 4 out of 7. If let's say you actually used a green shirt on Monday, okay, things change. Now, you still have the 4 blue available, so we have 4 out of 7. But since you already used 1 out of the green ones, 1 out of those 4, that leaves you with only 3 out of 7 shirts available in terms of green shirts. Okay. Now let's see what we're interested in terms of the problem. We want the probability that you wear a blue shirt on Monday and a green shirt on Tuesday. So analyzing my tree diagram, I want a blue shirt on Monday and a green shirt for Tuesday. Notice I can just multiply my probability. So this one is just a half times 4/7. So that will give me 1 times 4, it's 4, and 2 times 7 is 14. Let me go ahead and divide by 2 and 2 here so I can simplify this one. This is just 2/7. So the probability of wearing a blue shirt on Monday and a green shirt on Tuesday is just 2/7. In a similar way, since we know these events are dependent, what shirt you actually wear on Monday affects the choices for Tuesday available. We know that they are dependent. So we can use the following formula. We know probability of B intersection G will just be the probability of B or actually probability of wearing blue on Monday times the probability of wearing green on Tuesday, given that you already wore blue on Monday. Okay. Again, we know the probability of wearing a blue on Monday, it's a half, times the probability that you wear green given that it was blue, which is 4/7. And you'll get the 4/14 would simplify to the 2/7. So notice again, since we know these were actual dependent events, we could have used this formula. The probability of A and B, or A intersection B, is just the probability of A times the probability of B given A. Okay, so you have 2 different approaches for this problem. You could actually have used your tree diagram for that one, or you could have used your formula for dependent events. Okay, that concludes our video on probabilities of dependent events and tree diagrams. I hope you enjoyed. Good luck in your homework.